Welcome back to part 3 on zeros of a polynomial. In the previous sections, you've learned that an nth degree polynomial function can have at most n real zeros, or roots. For example, f of x equals x squared plus 1 has no real zeros. Because this is a parabola shifted up off the origin 1 unit. And f of x equals x cubed plus 1 has only one real zero because this is a cubic shifted up 1 unit and therefore has one real zero to the left of x equals 0. It crosses the x-axis at this point. The following theorem sheds more light on the number of real zeros of a polynomial. This theorem is called Descartes' Rule of Signs. First, let's let p be a polynomial with real coefficients. The number of positive real zeros of p of x is either equal to the number of changes in sign of p of x or less than that by an even integer. And the even integer thing we'll talk about very shortly, and hopefully that will make more sense. The number of negative real zeros of p of x is either equal to the number of changes or variations in sign of p of negative x, notice the negative there, or less than that by an even integer. Again, very important to note less than by an even integer. We have to define why we have to take it in pairs of 2. The reason is if it's not a real zero, it's either a complex conjugate pair or it is an irrational conjugate pair. So let's talk about what a complex conjugate pair looks like. Complex numbers are your imaginary numbers. So this would be like x equals 1 minus I and x equals 1 plus I. You could also have some radicals thrown in there, but this is an idea. See how the conjugate pair has a negative I and a positive I? That makes it a conjugate pair, plus and minus. So we've already talked about irrational conjugate pairs. You just didn't realize that's what it was. This is like x equals 2 plus or minus root 5. These are irrational conjugate pairs where the plus or minus gives you a pair. And I like to say it's a conjugate pair, just like shoes come in sets, a left foot and a right foot. You get conjugate pairs for complex zeros and irrational conjugate pairs. The shoes look different, but there's still a pair of them. So let's try an example now that we've kind of talked about how you can find how many zeros to expect. Exercise 4. Use the Descartes rule to determine the possible number of positive and negative real zeros of the polynomial. For the positive real zeros, we just look at the sign changes. So there is a plus in front of the 3x to the third, and it changes sign from the degree 3 term to the degree 2 term. It changes sign again from negative 5x squared to positive 6x. And it changes sign again from 6x to negative 4. So there are 3 sign changes. So we would say that there are, since all the signs alternate, we would say there are at most 3 positive real zeros And since the degree is 3, that's convenient because that's as many real zeros as you could possibly have. And it is either that or less than that by an even integer. So the other option would be 1 positive real zero. And you may be wondering, Sarah, why am I ever going to use this? The answer is try it in your calculator, graph it, see if it works. That will throw out a lot of possible options just by using your calculator. But this is another method to throw out possible real zeros. Okay, so now let's check for negative zeros, p of negative x. And notice I'm substituting a negative in, so now I'll have 3 times negative x quantity cubed minus 5 times negative x quantity squared plus 6 times negative x minus 4. So this will give me a negative 3x to the third, getting rid of that negative x inside the parentheses. This will be a negative 5x squared, a negative 6, and a negative 4. Notice that all these signs are negatives. There are no changes in sign here, which means there are no negative real zeros. Now let's look at example 5. First, let's check for changes in positive sign. So positive, 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 positive. There are no changes to p of positive x. So since there are no changes in sign, there are no real positive zeros of p of x. Now let's talk about p of negative x. This will check for our negative zeros. Substituting negative x to the fourth plus negative x raised to the third plus negative x raised to the second plus negative x plus 12. Simplifying, we will have x to the fourth minus x to the third plus x squared minus x plus 12. If I look at how many changes in sign there are, I go from a positive to a negative, from a negative to a positive, from a positive to a negative, and then from a negative to a positive. So there are 1, 2, 3, 4 changes in sign. So there are at most 4 negative real zeros of p of x. And then you can say, because there could be either complex conjugate pairs or irrational conjugate pairs, we could say or 2 negative real zeros, or 0 negative real zeros. Now you can stop this video now if you kind of get the idea, but I'm just curious. I want to graph this and I want to see how many real zeros there actually are. So I'm going to grab my calculator And I'm going to type this thing in because I'm curious and I want to see what's going on. X to the 4th plus x to the 3rd plus x squared plus x plus 12. I'll graph that. Nothing. So I'm going to zoom out and see if I can see something further out. Okay. So I can see something going on toward the center. So I'm going to change my window so that my x's go from -10 to 10. And everything else stays the same. Let's see what this looks like. So it has this interesting parabolic shape. It's opening upwards, which makes sense. I think I still will change my window a little more. I don't need anything below the x-axis. So I'm going to change my window so my y-min is at like -2 instead of -40. And then it also looks like I only need to go from like -5 to 5 for my window. So it's doing something very kind of strange here. It looks like it might come down, bump back up, and then down again, but it never is crossing the x-axis. So from that information and the information I just gathered using Descartes' Rule of Signs, I can say that this is the true statement. There are 0 negative real zeros. There are also no real positive zeros. They are all complex zeros, which is very interesting. I think that that's helpful information. You could do the same type of process with the previous example I showed you and find out how many actual real zeros there are.